Hello. Yes, privileged to be here and speak about the recent Basecaller advancements we've delivered. And everything I say today is going to be using released models and chemistries, so will be available for you to use. All right, so starting with DNA, our current suite of models are known as the V4 set of models, and we've now moved on to the V5 suite, as you'll see at the top there, for reasons I'll go to later on in the talk. Starting with accuracy. Here we have the accuracy for the previous generation of models, V4.2, the current generation of models, V4.3, and the new generation, V5. So we see a 1.5 Q-point improvement, which is pretty great accuracy jump. And again, it just needs you to update your software models, and it's available for you to use. This accuracy improvement also follows through to other data types. So here we have a set of bacterial isolates. The accuracy on the y-axis is comparing a nanopore-only assembly to a hybrid assembly. And on the x-axis, again, we have our 4 different generations of models. We see a big jump from V4.2 to V4.3, but we also have another nice increase going from V4.3 to V5 SUP. And these accuracy improvements also follow through to our variant calling. So here are our results for all of the different variant calling metrics, SNPs, indels, structural variants at 30, 60, and 90 depths for the new V5 SUP model. But one area we've made massive improvements recently is in indels. So this graph looks at indels, the y-axis being the F1 score and the x-axis being depth. And we see an up to 2% increase in improvement going from V4.3 in the black line underneath to V5 at the top, which is remarkable. And that's a 28% reduction in error, and again, available for you to use. So we see nice improvements at specific regions. You'll also see improvements in homopolymers and low complexity regions that we haven't shown today. And we see that it's single read accuracy, but also at assembly level, which we'll see later on in Sean's talk. That's DNA. Moving on to RNA. So this is our current RNA SUP model, V3. And then this is a V5 SUP model, so a nice jump, but as sort of Susie alluded to, we've gone even further, and this is the new V5 SUP model. So we see a 4.3 Q accuracy improvement, again approaching Q20, which is remarkable. It's such a huge jump, and available for you to use. All right, so how do we keep delivering these improvements? So I'm going to introduce the training and validation engine as one side of this. And because we're a talk about basecallers, I'm going to sort of focus in on the basecaller side of things. So I've divided it up into 3 sections. We have the basecaller model section on the left-hand side. We have basecaller analysis on the bottom, and then downstream models at the top. We're going to look at each of these 3 areas, give you an overview of how our systems and processes work to train and deliver all of our production models, including the basecaller, and then quickly walk through some improvements so you can see where certain things have come from. For the basecaller model, we take a diverse set of signals from a variety of different species, as well as the corresponding references, and then basecaller them and align them to produce a data set. Once we have our data, we then do an analysis to make sure everything looks good, accuracy, speeds, lengths, coverage, etc., etc. If it passes these checks, we create a training set. With our training set, we use our open source software called Bonito to train our basecaller models and deliver our fast hack and SUP models. We then take these models and put them into our basecaller analysis pipeline. So we have an increasingly extensive suite of basecaller analysis. So we have read level metrics. So these look at specific reads for things like accuracy and coverage and so on. We have pilot level analysis. So it's looking for specific improvements or changes in sequence context or on sort of a bias on the strands. And then if we want to look at anything, we also use tools like IGV to do manual inspection. And then we also pass our basecaller models over to the ONT application team, so Sean, etc., to do some more real-world usage to see, okay, this is improved, this is amazing, or you should look here with your tools and IGV and so on to see what's going on. Again, if everything looks good, if all the analysis comes through, we then go on to our downstream model section. So this includes things like base modifications, variant calling, consensus, stereo duplex, and so on. Each of these also has its own training section, so that's represented by the grey box on the right. And they also all have an extensive suite of analysis. So you can see the space of everything we do to deliver these models is quite large. So if we focus in on sort of starting from a Basecaller model and following through and thinking how do we keep delivering improvements? Well, if we look at our signal, we've recently done the E8 2.1 update, so all of our signals have improved. Our references increasingly improve, which becomes important as we begin to reach very high simplex accuracies. Our training set increasingly becomes diverse in both species and modifications and so on. That goes through to our models. As I said, our analysis suite is becoming more and more extensive, but it's also becoming automated. So our iteration times are reducing, and sort of the range of analysis we can do on all of our different models is expanding. And then as all of these things lead to improvements in the Basecaller models, they tend to follow through to our downstream analysis. But we also look at the downstream analysis tools. So, for example, for Claire 3, to get our variant calling indel, we did work on improving the training optimization dynamics there, which led to the large improvement, coupled with the improvement from the V5 model set. So that's an overview of our training and validation engine. The other thing that we've done to deliver the big improvements is change the architecture of the SUP model. So, as you may have guessed from the slide, we've moved on to a transformer architecture, whereas the old model was based on LSTMs. We're going to look at the current architecture and then do a look at the V5 new transformer-based architecture so you can see the difference. So the current architecture is on the left-hand side here. We start with a signal at the bottom. We apply a set of convolutions to extract useful features and downsample the time domain. And then we apply a set of 5 alternating forward and backward LSTMs before decoding into the most likely base sequence. If we zoom in on one of those LSTM blocks, we can see that it's autoregressive. So on the left-hand side is a state, and at the bottom is the current input. And that's used to produce a new state on the right-hand side and an output pointing up there, and then it goes on to the next time step in the sequence. If we compare that to the new transformer architecture, we see that the LSTM blocks have been replaced with, is now 18 transformer encoder blocks, and the convolution stack and the decode stack have remained relatively unchanged. Focusing in on the transformer encoder block, we see that there's 4 different parts. There's the multi-head attention at the bottom, then a normalization, then there's a feed-forward layer, and then another normalization. All of these can operate in parallel, so there's no autoregression like the LSTMs. And if you want more information, there's going to be a blog post out, but we also have the implementation in Bonito and Dorado that you can look at and inspect. Okay, so to summarize, we've seen big increases in DNA accuracy, a huge increase in RNA accuracy. Our SUP architecture is switched to transformers, and all of this is available in Dorado now. So, thanks very much.